Hello and welcome to Coffee Table Physics. I'm Riley.
And I'm Jonathan. The reason you're probably watching us right now is because you wondered, like us, how do magnets actually work?
I mean, why do only some pieces of metal attract or repel each other? Is it magic?
No, it's physics. Now, the most fundamental answer as to the origin of magnetism will probably annoy most of you.
Because it's just a property that the constituent parts of matter possess, like the property of mass. It just is. All subatomic particles, most notably electrons, are like microscopic magnets and have an intrinsic magnetic moment with a particular size and direction. This describes how a particle moves under a magnetic field, and in turn how it generates its own magnetic field. But why are most materials not magnetic?
Well, let's start with looking at the structure of the atom, the things that make up stuff. We have a nucleus at the centre and electrons, the things that make electricity work, whizzing around the outside. Now, the magnetic moment of the nucleus is quite small in relation to that of the electrons, so we can kind of ignore its effect.
The electrons orbit at different distances from the nucleus in regions called shells. Here is where an object reaches the first barrier to being magnetic. In fully filled shells, we see an equal number of electrons, with magnetic moments pointing in one direction as pointing in the opposite direction, and so the magnetic effect is cancelled out.
Some of you may ask, but moving charges generate magnetic fields, so why don't we see a field from the orbiting electrons?
Well, it turns out that these also cancel, as the orbiting electrons move in different directions.
Half-filled shells usually have unpaired electrons with magnetic moments pointing all in the same direction. If you have an atom with a half-filled outer shell, you might be able to make a magnet out of it. Atoms in these regions of the periodic table are potential candidates.
Okay, so anything made of these elements are magnets?
Not so fast. Even if I have an individual atom with a net magnetic moment, if I put it next to an atom with a net magnetic moment pointing in the opposite direction, the two cancel out.
You see, if we have a collection of atoms with net magnetic moments, they can arrange themselves in one of two ways. In anti-ferromagnetic materials, the directions of the magnetic moments will alternate, meaning they will cancel out. No magnet.
If, on the other hand, you have a ferromagnetic material, like iron, all the moments will align themselves to point in the same direction.
Yes! Finally, we still have a net magnetic moment. But which category the material falls into will depend on which configuration minimises energy.
Yes, nature is very lazy.
But hang on, I hear you say, I've seen things that are made of iron that aren't magnetic. Don't worry, we haven't been lying to you. There is just one more requirement needed for a material to be magnetic.
You see, a ferromagnetic material, say a lump of iron, may consist of many different chunks called domains. In each of these chunks, the individual atomic magnetic moments point in the same direction, giving them a net magnetic moment. However, neighbouring domains have magnetic moments pointing in different directions.
Damn, our magnetic moments have been cancelled out again. But, luckily, all is not lost. If I apply a strong enough magnetic field pointing in a particular direction to this ferromagnetic lump, I can help the domain with the moments pointing in that direction to increase in size and overcome all the other domains until we have a lump consisting of atoms with magnetic moments all pointing in the same direction. Finally, we have a magnet.
You sure? No more hoops we have to jump through?
Thankfully not.
So, in summary, if you can give me a material composed of atoms with half-filled electron shells, with all the atoms aligned, and with all the domains aligned, you've got yourself something magnetic.
And so, we reach the end. Now, next time you're playing around with your fridge magnets, you'll know what's holding onto that picture that you drew when you were 5, but your mum won't throw away.
Thanks for joining us. If you have any comments, feel free to leave them in the comments box.
Plus, tell us if there's something about this wonderful world around us that you think, I want to know what's going on here. We would love to help.
See you here next week.
Same time, same place. Cheerio!